Bueno, vamos a empezar. Bueno, bienvenidos a la edición de otoño del coloquio del departamento. El conferenciante de hoy es Xavier Cabré, de ICREA y la Universitat Politècnica de Catalunya. Xavier completó la licenciatura en Matemáticas en 1989 en la Universidad de Barcelona. Después se fue a Estados Unidos a hacer la tesis y la hizo bajo la supervisión de Nuremberg en el Instituto Courant. La defendió en el año 94. Y después ha hecho etapas postdoctorales en el Instituto de Estudios Avanzados de Princeton, en la Universidad Pierre-Marie Curie en París. Y después regresó a Barcelona con una plaza de profesor titular en la Universitat Politècnica de Catalunya. Aún se movió a la Universidad de Texas en Austin durante un periodo de un par de años y finalmente, de manera definitiva de momento, se mudó como profesor ICREA. Bueno, no sé, como profesor ICREA en el año 2003 se unió a la Universidad Politècnica de Catalunya y allí sigue. El trabajo de Xavier ha sido reconocido de muchas maneras. Fue nombrado Fellow de la American Mathematical Society en 2013, que es la clase inaugural. Ha sido conferenciante plenario en muchas conferencias prestigiosas. Voy a decir solo el European Congress of Mathematics del año 21. Ha realizado labor editorial en revistas muy prestigiosas, por ejemplo la revista de la European Mathematical Society, pero también la de la Universidad Autónoma de Barcelona, la Publications Mathematics, donde sigue, Calculus of Variations en PDE, Potential Analysis y algunas otras. Ha dirigido hasta la fecha, y si no me equivoco, 11 tesis doctorales que se hayan completado. Y bueno, el área de investigación de Xavier son las ecuaciones en derivadas parciales, elípticas y parabólicas, estudia propiedades cualitativas de soluciones y en los últimos tiempos también se dedica a cosas que tienen que ver con la probabilidad porque estudia problemas de estos de reacción con difusiones fraccionarias que tienen saltos y entonces tienen cuestiones probabilísticas interesantes, de las que yo aprendí la semana pasada en un congreso que hubo aquí. Ha publicado en todas las revistas en las que a mí me gustaría publicar. Y bueno, hoy nos va a hablar del 19º problema de Hilbert. Xavier.
Muchas gracias, José, por la invitación, por la introducción y gracias también a todo el departamento y en especial a Fernando, que es creo quien ha impulsado un poquito más esta idea también del mini curso que he dado esta semana, que ha sido un gran placer. Y bueno, me hace mucha ilusión poder dar este coloquio aquí y lo di la semana pasada, está recién preparado de hace 2 semanas, o sea, solo lo hice la semana anterior en Bilbao para prepararme para hacerlo mejor aquí. No les digáis a los de Bilbao, pero I will speak in English during the talk, okay? But since I want to say some words about Ireneo, I would like to say it in Spanish. O sea que me hace mucha ilusión. No pude estar en el congreso para Ireneo y por eso me hace especialmente ilusión poder dedicar este coloquio en su memoria y solo decir que bueno, que cuando pongo una foto así todavía me impresiona bastante y que lo encuentro a faltar mucho. O sea, básicamente con Ireneo era cuando nos veíamos periódicamente, ¿verdad? Era un sentimiento de felicidad. Yo diría, básicamente el sentimiento de felicidad mía. Tenía el sentimiento de que era mutuo. No sé si será verdad o no, pero yo al menos tenía esa impresión. Y eso es muy importante y creo que había una admiración mutua y un disfrutar estando juntos y siempre, bueno, sus sonrisas. Entonces, bueno, yo de Ireneo aprendí, aparte de esto, aprendí en el Courant de Nuremberg, claro, aprendí muchas matemáticas, pero lo que es el día a día y las vicisitudes y muchos aspectos de lo que es el mundo universitario, la investigación, lo aprendí de Ireneo y de Juan Luis, que estaban juntos organizando mil cosas. Y ya antes de irme yo a Nueva York, ¿verdad? La primera escuela, mi primer congreso fue una escuela de verano, justo el 89, cuando acabé la carrera. Un profesor, August Palancas, un profesor un físico, que nos había dado ecuaciones de derivadas parciales del quinto año de carrera, dijo, voy a ir a esta escuela de Santander y tal. Yo me dediqué a las EDPs porque Carlos Simó dijo, aquí en Barcelona no hay gente haciendo ecuaciones, deberías estudiar esto, y le hice caso. Y entonces fui a Nueva York. Con Ireneo y Juan Luis aprendí lo que es organizar cosas, invitar a gente, tener criterio de lo que es un cierto nivel científico y otro nivel científico, entusiasmo, apoyar a los jóvenes, todo esto lo aprendí de ellos, así, ya antes del curso, y luego durante la tesis venía a menudo y lo seguía aprendiendo. Bueno, y quería decir que muchas gracias, Fernando, por regalarme este libro, porque me hace muchísima ilusión, de verdad. Sé que Guillermo estuvo trabajando en él.
No, pero tienes que estudiarlo.
Sí, por eso lo estoy abriendo. Ahora no tengo tiempo, pero ya lo abro.
Ya hago el libro.
Fabuloso. Gracias. Bueno, pues vamos a por ello. Si tengo tiempo al final, que no estoy seguro, os hablaré. If I have time at the end, I will describe some recent results of me with Alessio Figale, Xavier Rosotón, and Joaquim Serra. And this is not the paper by them. This is a paper by me that you can find in archive, where I improve some of the proofs are now here better, are quantitative proofs. And I'm very glad to dedicate this. It's like a survey. It can be read by a PhD student, starting PhD student. You don't need to know, not even the Sobolev inequality. So it's written to be read by students, very easy, and it contains all the proofs. So it's like a survey. And it's dedicated to Ireneo. Okay, so let's start with I hope you will learn some things, historical things. Let's go to 1907. Independently, Ries and Fréchet proved a theorem, right? That we call it Ries-Fréchet. That says if you have a Hilbert space, given a continuous linear form, there exists a unique vector in the space, in the vector space, in the Hilbert space that represents a form. Everybody knows this. This is a correct statement, but it's not complete statement. The theorem should never be stated like this, in my opinion, and in Brézy's opinion also. It has to be stated with all the information that it gives for further possible implications and use of it. And the correct theorem to be stated is now in blue. In addition, it is characterized by being the unique minimizer of a functional that is 1/2 of the norm square of a vector minus the linear form, a quadratic term and a linear term. It's the unique minimizer of this functional that sometimes we call it energy, but it's a functional. Let's prove it. The proof is very short, but but it contains a lot of important things. And this is the proof that I think that books should give, not the one that we will mention later. At the end, it's the same, but let's prove it. Since the functional is bounded below, which is very easy because the continuous form, the form is continuous, I can define the infimum. And once you define the infimum, there is always a sequence of vectors that will converge towards infimum. That we call a minimizing sequence. So let UK be a minimizing sequence. Claim UK is a Cauchy sequence. We'll prove it in a second. Consequence, Hilbert space we impose to be complete. If it's a Cauchy sequence, it converges to somebody, and by continuity of the functional, the energies converge, and therefore U is a minimizer. And you are done pretty much, because then what you do, you say, if U is a minimizer, when you compute the functional in neighborhood points, vectors, the derivative will be 0. When epsilon goes to 0, you develop this, it's just trivial, and you get that this will be 0 for every vector. U represents the form. Prove that it's Cauchy. Okay, this is something very important. The proof should start like this, because this student should learn like this, because this is done also in nonlinear problems. The Italians know this very well. When you have a minimizing sequence and your problem has some kind of convexity or quasi-convexity, if you have two vectors that minimize or almost minimize the functional, make the average, because probably it's better. Probably it's better. So we start like this, and we start, since M is the infimum, you will have like this. What is the energy of the average is written here. Now, if you develop this, there is UK squared that will be in the energy of U, UM squared, but there will be the scalar product, UK UM. To kill this, I will add and subtract the difference between UK and UM. I just add and subtract. These are all equalities. And therefore here, when you develop this, the scalar products will go away. So I keep this term here with an 8, okay? And here, they disappear, and what you get is modulo 1/2, the energy of UK and the energy of UM. And therefore, when K and M goes to infinity, well, this is not correct like this, because I should say that this goes to the lim inv or the lim sup. I take limit. Sorry, this is not correct written like this. This goes like this goes to m over 2, m over 2. This is m. This is m. This goes to 0. You see, I didn't write it well, but you see the proof. It's Cauchy. Several people, sometimes people tell me, no, I don't prove it like this, I prove it using the projection into a convex set. Said, okay, you should not. But if you do, don't worry. Anyway, the projection into a convex set, the proof is the same, and there is also a minimization problem behind. If somebody knows a proof of the theorem that doesn't use minimization, please let me know. I will not be interested on it, but but let me know with the axiom of choice or whatever. This is the good proof. Good. Now we will speak. I will read and I will explain things that that if you go to Google you will not find. And I tried, and I spoke with Breziz about this. And that you will find in this beautiful paper by Breziz and Browder at Rutgers from 1998, Partial Differential Questions in the 20th Century. And they cover a series of topics, important topics of PDEs and analysis in the 20th century. And Breziz personally told me that, I think at that time Browder was retired or almost, so he had a lot of time. He could read German, and they spent a lot of time, Browder, but also Haim, reading the articles of Hilbert and of Poincaré and Riemann and many people. Okay, so we have to trust. I trust this reference. Okay, from Breziz and Browder, 1898. Now let's go back from 1907 to 1833. 70 years. They write, an extremely important principle was discovered by Green in 1833 for the Laplace equation. He observed that a solution of the equation harmonic function in a domain of R3, which assumes a given boundary value phi on the boundary, later called the Dirichlet problem, minimizes the integral of the Dirichlet, and what we call the Dirichlet energy, so sum the gradient square integrated in omega, minimizes among all functions which have the same boundary value phi on the boundary. Here realize this, green. On the other hand, if there is a minimizer u tilde which is smooth, then it will be a harmonic function, if there is a minimizer. Related arguments were carried out independently by Gauss. Their work was followed by Thomson Lord Kelvin in 1847 and by Riemann in his thesis in 1851, where he named this approach the Dirichlet principle. Do you know why? Because Riemann learned this problem from Dirichlet, because Dirichlet was his professor. Simply because of this. And then he called it the Dirichlet principle. Dirichlet, we don't know if Dirichlet knew that this was coming from green, or if he didn't know it, or if he knew it, he just didn't say anything, okay? But anyway, we call it Dirichlet principle, but this green principle, okay? So, problem, given a boundary value, as nice as you want, or say we will be concerned with continuous in a nice domain, is there existence of solution of this problem? This was not known at that time, 1833. If I extend the boundary value to all of omega bar, and I call it phi still, and I compute the Laplacian, the difference of u tilde with phi will be 0 on the boundary. So if you don't like that problem, or if you prefer this problem, you will have to solve 0 boundary value, and you will have to solve the Poisson equation instead of the Laplace equation. Now let me do something that you know, but that at that time they didn't know, in this way. Or multiply this by a function that vanishes on the boundary and integrate. Integrate by parts, that is the green theorem, right? And you will get grad u, grad v, and this is like a scalar product. And this will be, it's a linear form. So it looks like a Riesz-Frechet theorem. So the solution here, instead of minimizing the Dirichlet energy, it should minimize the Dirichlet energy minus the linear term, like in Riesz-Frechet theorem. Right? So now, let's go back to this is 21st century, or 20th century, but let's go back to 19th century. So at that time, right, 1833. Questions, well, later. So the second half of the 19th century. Is there solution? Two questions. Is there solution of this problem? Or the other one? Another question. Is there a minimizer of this problem? Of course, if I prove that there is a minimizer, I will have a solution. And if I prove that there is a solution, I may not know still if there is a minimizer. Well, or how to, well, yes, but I may not prove the existence of minimizers by a direct method, useful method. So, how does this story continue? First, I keep reading Brézis' brother. In 1890, Poincaré gave the first complete proof in rather general domains of the existence and uniqueness of a solution of the Laplace equation for any continuous Dirichlet boundary condition. He introduced the so-called balayage method. This iterative method relies on solving the Dirichlet problem on balls in the domain and makes extensive use of the maximum principle and Hartman's inequality for harmonic functions. Balayage is like to brush the or push the singularities towards the boundary. This is like a potential method theory similar to Perron's method also. No minimization, right? It was important, the thing of continuous boundary condition, because they knew that harmonic functions had to be infinity and analytic inside. And they were worried very much, until Hilbert, you will see later, they were worried that if the solution is going to be analytic inside, is it possible that to solve only with a continuous boundary data that is not analytic? And they were really worried about this. He gave the first proof, Poincaré. Okay, this was not really, I think was not very, Brezis told me that was not even clear that he was the first to prove it before they did this historical work. But more things, more surprising things. Maybe this you knew. Okay, that's the paragraph we read. Then, in 1900, Hilbert states some problems, and we'll go back now, we'll stay with Hilbert for a while. The normal thing would be that this goes first. This is called, the 20 is called the general problem of boundary values. This means, is there existence, because Poincaré's before is 1890. It's 1890. Okay, that's why he puts it for boundary, for the general problem. By the general problem, he means not only the Laplace, but other equations, I think, okay? And the 19th is, are there solutions of regular problems in the calculus of variations always necessarily analytic? This was known for the Laplace, but not for other equations that will appear later on, more general equations, more general functionals, right? Okay, these are the Hilbert problems. So now the most interesting slide, in my opinion, 2 slides, is this paragraph from Brezis' brother, and I'm just going to read it. In connection with problem 20, Hilbert revived the interest in Riemann's approach to the Dirichlet principle. Hilbert revived the interest. The methods originally proposed by Hilbert during the period 1900-1905, 1907 is Ries-Fréchet. 1905, for the Dirichlet principle, are complex and difficult to follow. Brezis, okay, I will say it later. But gave rise to an extensively attack by numerous authors, including Beppo Levi, Henri Lebesgue, Fubini, Zaremba, Tonelli, Curran, an attack which was very fruitful in creating new tools. The methods originally proposed by Hilbert. The original suggestion of Hilbert was to take a minimizing sequence for the Dirichlet integral and to prove that an appropriate modified, regularized, appropriately chosen sequence converges uniformly to a minimizer. A variant of this approach was carried through a few years later, rigorously, for first time, by Zaremba, using a modified form of the original minimizing sequence. Another version was presented by Curran. These arguments, following Hilbert's original suggestion, rely upon a compactness argument in the uniform topology, namely the Arzelà-Ascoli theorem. Let's forget about this of the Lebesgue integral, because which year did we say that it was the Lebesgue?
1902.
1902 is the Lebesgue, okay? Okay, doesn't matter now. But you see, the Hilberts, Nirenberg told me that he read these papers, including the ones of Hilbert, that there are many ideas that are wrong. I mean, that cannot work, okay? That cannot work. That now we know that cannot work. There are even mistakes in some papers by some of these authors, including Hilbert. But when they wrote at the end, you see that Brezis, a brother, give a lot of credit to Hilbert, being himself the one who is suggesting to this program. But this program relied on that minimizing sequence, we change it, we modify it, we regularize it, and we use Arzelà-Ascoli. And then it's incredible that among the other community, we don't know, many people, most people, even Italians, Matteo, don't know this, not you, many others.
Not only you.
Not only you. It was Beppo Levi who first observed in 1906, not 1907, Ries and Fréchet, 1906, that a general minimizing sequence for the Dirichlet integral is a Cauchy sequence in the Dirichlet norm, and therefore converges in an appropriate completion space with respect to the Dirichlet norm to a generalized function, and so minimizer. So when we say Ries, Fréchet, and Lax, Milgram, and all this to our students, if we trust Brezis and Brother, we were lying, okay? It's not, it's Beppo Levi. And this for me is very, 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 this is the origin of Italian calculus of variations, I'm sorry. And this is it's very smart to realize that this sequence is Cauchy, okay? It's the birth of the Italian school, and it's the birth of functional analysis. Because probably I don't have time to, I'm not an expert of history of math, but I would say that the theorem of Reed-Séché is the origin of function, is the first theorem really in functional analysis, at least in Hilbert spaces, that they independently discovered thanks to that 1 year before Levy realized this and distributed the idea. Okay? And yesterday, speaking about this with Fernando Mateo, said, yeah, because what about, I had never thought of this, what about the name of functional analysis? Why functional analysis? Because functional analysis is vector spaces with a norm, right? So it's, and then linear maps, operators, operator analysis, okay, yes. Functional analysis, no, functional analysis should be calculus 1 or calculus 2, because calculus 1, calculus 2 is what deals with functions. But functional analysis doesn't deal with functions in general, but deals with functionals. Deals with functionals. So analyse fonctionnel, because they had to analyze the fonctionnel, the Dirichlet. Okay. Right? I think it makes sense, right? Makes sense. Good. And now here is our hero, right? At least my hero, Beppo Levi, who was Jewish, was from Turin, like Matteo, right? He was in different universities, and at the time when he was in Bologna, the fascists arrived, and Mussolini was there. All professors in Italy were, Jewish professors in Italy were expelled. And then an engineer, Cortés Pla, from Rosario, invited him to go there, and he emigrated there. And then he spent the rest of his life in Rosario. And in Rosario, he met the best ever Catalan mathematician, that is a geometer named Luis Santaló, who was not Jewish, but was from Girona and was Republican. And he decided before the Civil War to go to Argentina. And he also went to Rosario. And then they met, and also with other people. And they have, Levi and Santaló have papers together. Beppo Levi have papers in Spanish, leyendo Euclides, of course, because he spent all his life, many years in Rosario. And they also work with the best, it seems from what I heard, mathematician from Uruguay, José Macera, and this is Santaló and Levi together in Rosario, starting something new in Argentina, something new and powerful. And then later Santaló moved to Buenos Aires, but Levi remained in Rosario. And then let's read the person who can inform about us about this better, about this story of Argentina. Who is the person who can inform us about this better? Well, Luis Caffarelli, and Ireneo would be also happy. And finally, this is a great interview that I recommend for you, because there are so many interviews. This is very recent, after the Abel Prize, it was made in Oslo, an interview to Luis. And I extracted this, one of the answers of Luis. So these are words of Luis Caffarelli. It says, as a student, I was heavily influenced and inspired by Luis Santaló. This I know because personally Luis Caffarelli had told me this, that Santaló was the one who impressed him more. I don't know if the geometric approach of Luis Caffarelli sometimes comes from this, because he was a geometer, or maybe also his genetics. But okay, he was influenced by Luis Santaló, Manuel Balanzat, and Carlos Segovia. Santaló and Balanzat were both Spanish mathematicians who moved to Argentina as a consequence of the Spanish Civil War. Santaló made important work into integral geometry and geometric probability, while Balanzat worked in functional analysis. They built, jointly with Reis Pastor and P. Calleja, a superb undergraduate and graduate mathematics program at the University of Buenos Aires, uniting a very strong group in analysis, geometry, and algebraic geometry. The harmonic analysis Segovia, right? Segovia was a prominent graduate from Universitat de Buenos Aires who did his PhD at the University of Chicago with Alberto Calderon, who is, not here, who is ad honoris causa by this university, like Luis Caffarelli, like Jaime Bresis also. While closer to me in age than Santaló and Balanzat, Segovia was always a strong support for Luis. Okay, so now we know a little more also. So the thing, the harmonic analysis and PD's School of Argentina comes from, well, the origin is Levi and Santaló, if you wish, okay, and Rey Pastor. Okay.
Is it true, according to you, that Luis Caffarelli was the first Argentinian that combined harmonic analysis methods with PDs?
Do you think it is true?
I think so.
Good, so then me too. Well, I thought that me too.
Okay, thank you.
Okay, so Beppo Levi inaugurates functional analysis, right? And the Hilbert representation theory and all this, and that's 1906. And then we have to wait 50 years for the other problem of which one it is? The 19th problem of Hilbert to be pretty much solved, which is the problem about the analyticity or the regularity of minimizers for more general functionals. Functional. So what are the functionals? The functionals are these. Let's look here, and now we will read here. The functionals are these. Now I'm going to integrate, instead of the gradient square, another convex function of the gradient, which is not the quadratic one. Okay? And this guy L will be called the Lagrangian. Okay? The Lagrangian. So this theorem was proved 50 years later, but independently by De Giorgi and Nash. Okay? I'll tell you the story of Nash after the talk if you like to know the story why Nash solved this problem. Okay? It says, let omega be an open set in a Rn, consider functions defined up to the boundary, let L be a uniformly convex, this is very important, smooth, uniformly convex function, which means that the Hessian computed at any point Q in a Rn, it's positive definite with eigenvalues between small lambda and capital lambda. The constants small lambda and capital lambda are given. L is called the Lagrangian. Then, if there is a minimizer of the functional among functions that agree on the boundary, like always, we have that U is smooth. If L is smooth, and if L is analytic, U is analytic. Okay, so this solves the Hilbert problem, 19th problem, for uniformly convex function. Also imagine like a quadratic, and you perturb it a little, but it stays uniformly convex. Let me go a little fast and tell you how the proof goes, okay? Because I want to do other things. First of all, you do the Euler-Lagrange equation like what we did with Luis Freche. You do it, and what you obtain is an equation in divergent form but non-linear. dxi of the ith derivative of the Lagrangian, but this is just a function, computed at gradient u equals 0. This is non-linear because Li is not going to be a linear expression, all right? Unless you are with the Laplacian, that means the Dirichlet energy. Okay, it's a non-linear equation. Then what you do is to look at what the first derivative satisfies. It's a very typical technique in PDs. Let's look at what the derivatives satisfy. Well, you differentiate with respect to xk, you commute with xi, the xi is here. Now I have to differentiate with respect to xa. Well, the li differentiated twice, now with respect to j, and the jth component I differentiated with respect to xk, or the xk with respect to xj. Therefore, v, the partial derivative with respect to xk, solves this equation, where here there is still u, but now we will do a trick that it may work or may not work, depending on if you are lucky or not. And this is what was not known to do. This is what people were. Let's do it. Let's assume that we have a minimizer, u. If you have it, you have it. And then you can compute this matrix at every point, Lij, and I will call it Aij. And I will forget that it comes from you. It's just a matrix at every point. And it's uniformly elliptic, what we call uniformly positive definite, by the convexity of the Lagrangian. And therefore, what you can think is that V is a solution of a linear equation, but with coefficients. And the coefficients, I may not assume them to be continuous, since I still don't know, because they depend on the gradient of u, and I don't know if u is C1. In fact, that's what I want to prove. And if not, I would enter in a circle, vicious circle, that I would not arrive to anything, okay? Therefore, the first derivative satisfies a linear equation in divergence form, because this is written in divergence form, uniformly elliptic, great, but with bad coefficients, bounded measurable coefficients. That's how we speak, how we call these equations, okay? And then it was the Georgian Nash precisely who proved that every weak or distributional solution to an equation like that, uniformly elliptic with bounded measurable coefficients, symmetric, where lambda and capital lambda are constants, must be Woodholder continuous. And then and this is the big difficult theorem that since in the first half of the 20th century, many people were trying to prove, including my thesis advisor. It was one of his favorite problems, Nuremberg, and many other people, right? And the Georgi and Nash did it independently, right? And once you have this, then you are done with 19th Hilbert problem. Because if you minimize this, we know that V, now by V theory, V is C alpha. But if V is C alpha, means that U is C1 alpha. But then now that I know that U is C1 alpha, the coefficients are C alpha. And then linear theory, Schauder, potential theory, I mean, very easy, I mean, quite easy stuff and well known. Which year? 34, okay. V is C2 alpha, and you can get better and better regularity in this way, iterating, and you get to C infinity. Okay, the Giorgi proof is an elliptic proof, because it's Italian, right? Elliptic proof. It's based on an isoperimetric inequality. It has a geometric flavor, which is very nice, and it can be adapted to many problems. This is Luis Caffarelli's favorite proof. Nash proof is great. You can read it in a beautiful paper that my advisor, during the thesis, my advisor made me read, that it's called A New Proof of the Harnack Inequality Using the Old Ideas of Nash, written by Fabes, Struck, and Struck. And it's you don't need to go to the original paper of Nash. Fabes, Struck write beautiful. And they have this paper, and they have another one, Fabes, Struck, that it's called new proof of the reverse Holder inequality. And according to Nuremberg, these two papers were gold mines, minas de oro. So if you want to read them, still I think they are. The proof of Nash is very clever, because the heat equation is clever than us. The heat equation is super clever. The Poincaré conjecture has been proved with the Ricci flow. Why? Because the Ricci flow is super clever. Is more clever than the algebraic geometers, the PDers, the combinatorics, because the Ricci flow knows how to regularize things and make surfaces rounder and rounder and going to more constant curvature, which is the sphere. That is what you want to prove in the Ricci curvature, in the Poincaré conjecture. Nash used, instead of the Ricci flow, used the parabolic flow associated to the equation that here you have it, and use the right, it has a Green's function, solutions are given by convolutions, we like very much convolutions, and then you have to make the right estimates because you know that these coefficients are not good. He succeeded, and he uses the regularizing effect of the heat equation to prove that the solution, a stationary solution, will be better and better and better and better. And then later there was approved by Moser that it's based on the Sobolev inequality, which is also very useful, even that it's more calculistic, maybe not as important, say, but it is very useful to have. Now let's read this. The Georgi-Nash-Moser theory has been used since then for many nonlinear elliptic and parabolic equations. For most of them, there is a delicate first step to be carried out before being able to apply the Georgi-Nash-Moser, since the Lagrangian is often not uniformly convex. And this includes the P Laplacian and the minimal surface equation, for instance. First, you have to fall here, you have to prove that your equation is uniformly convex. So what does this mean? Let me show it to you. It's very simple. In the case of minimal surfaces. The theory of minimal hypersurfaces, by the way, in minimal hypersurfaces, I'm not speaking about Riemannian manifolds or anything. You have a hypersurface in Rn, all right? Has been and still is a main source of important methods and ideas developed in elliptic PDEs and in the calculus of variations, in particular since the year 60s. It has been, and it is still one or the main source of methods and ideas. Right? Everybody agrees? Antonio, do you agree? No? We agree, right? Luis Caffarelli agrees.
Okay.
Good. So then
It's better to know.
So let's look at minimal surfaces. Let's say a hypersurface. I tell all by my experience, hypersurface is nothing come locally. It is just the graph of a function. And since we are analysts, we like to have one function of one real variable function at hand and nothing else. And a hypersurface reduces locally to a function of n variables like before. All right? And the surface is the graph. You see here the picture, x, u of x. Beautiful. Here is the tangent plane. Very good. If there is a tangent plane, M is a minimal hypersurface when the mean curvature of the surface, which is the sum of the principal curvature, is 0 at every point. And this, for the graph, resumes in this PDE of second order, non-linear, that it's called the minimal surface equation. This equation is the Euler-Lagrange equation for one of the Hilbert's functionals, this one. By Pythagoras theorem. This is Pythagoras theorem, right? This is Pythagoras theorem. Square root of 1 plus radius squared. Let's see if it's uniformly convex or not. This is super easy. This is algebra. The Lagrangian is this. I just differentiated once. I differentiated twice. Just this is nothing to do. And you get something like this. You get the identity minus this matrix here, Qi, Qi, and then this. Let's write it on top of the solution gradu. Let's write it here on top of the solution. Oh, this is not a minus, this is an equal. This is an equal, huh? You get this and you get this. You see, when the gradient is very large, I can forget the 1. Because the 1 doesn't count, if it's very large. And therefore, this is a unit vector, and it will kill one of the eigenvalues 1 of this. So this matrix that will degenerate and will have n minus 1 eigenvalues equals 1, and 1 eigenvalue equals 0. So it degenerates when the gradient is very large. Therefore, this will be uniformly elliptic once I know that the gradient is bounded. And gradient bounded means that U is Lipschitz. So in minimal surfaces, you have to prove first, before being able to apply the Georgi-Nash-Moser theory, you have to decide if your surface is Lipschitz or not. And then you realize, we know, as we will see in a while, that there exist important minimal surfaces which are not Lipschitz, and even that which are not regular at a point, and these will be minimal cones. So to arrive to minimal cones, I decided to arrive to them from a simpler problem that is very easy to understand, and to make experiments, as you will see. We take two wires, right? We take, well, you know that minimal surfaces are the surfaces that soap. Well, I told that the heat equation is intelligent, but nature is even more intelligent than the heat equation, and everybody is more intelligent than us, right? But nature is even more intelligent because he knows how to produce minimal surfaces. The soap knows how to produce minimal surfaces. So you take two wires in blue, which are very close to each other, and you put them in soap. And there are several options for minimal surfaces. The green, which are two discs like this, that will have like a large area if the wires are close, and a catenoid in red that, of course, if they are very close, it has almost no area. Almost no area. So if they are very close to each other, then red catenoid has a smaller area than the two green flat discs. The minimizing minimal surface is the catenoid. These Japanese people, Department of Physics, I don't know if they are physicists or mathematicians, doesn't matter, they have a beautiful paper where they do an in situ observation of a soap film catenoid, a simple education physics experiment, but done very careful at their lab and making the pictures, okay, the photographs. They start separating, you start separating the wires slowly. And the soap you still see the catenoid. At some point, can we, at some point, no, but maybe there, because here you don't see, now you see. You see like here a bubble, okay? And then if you saw better, the film, if you do it carefully enough, the neck of the becomes very, very small. At some point, it makes like a bubble here, but it succeeds to create two discs. That's very funny, huh? The bubble is not in our, of course, it doesn't enter into the theory of minimal surface equation, right? Of course. Huh? Diego Cordova would tell us more things about this thing, but it succeeds to do that. So let's try to explain this. In fact, when they are very close, you would think that there is only one catenoid. Look here in red. Oh, the thick catenoid has a minimal area, less than the two discs. That should also be stable because the discs have zero curvature. So there is a absolute minimum, there is another minimizer. Ireneo would tell there must be a mountain pass, right? We don't know. In fact, here it is. There is another minimal surface, which is a thinner neck catenoid. Another catenoid inside. And it is unstable. And therefore, nature will not produce this guy. You will not see it. And you don't see it. Then you start separating the distance. What happens? At some moment, the catenoid, the thick catenoid, thick neck catenoid, has the same area as the two discs. Good. What happens if I separate a little more? Well, it is when you separate a little more, it is here. It's not the absolute minimizer, but nature still shows me this thick minimizer because it cannot jump from here to here suddenly. So, and this is to make publicity of stable solutions. This here is a minimal surface which is stable, but it's not the absolute minimizer and appears in nature. So we need to study them. The unstable you never see. And then at some point, At some point, you have here there is a minimizer, here there is an unstable mountain pass. At some point, it becomes an inflection point, and therefore, it's at this moment that the thick catenoid becomes unstable, and then it's when the disk goes away. And when they do the experiment, they measure the distance and they check that h is equals hc. That hc I compute mathematically, right? And the numbers are there in the paper. So this is very, very nice, right? Because it is very rich, very rich. Of course, the calculus of variations and the mountain pass, you should know that this starts from the study of geometric problems. This starts from when you have a compact manifold and you want to know how many closed geodesics there are. And here it starts the theory of Morse index and the Lister-Minkes-Schneiderman and the mountain pass and things like this. If there are two minimizers, there should be a third critical point. And then after geodesics, minimal surfaces, right? Well, the thing in blue, I already said it in words, and this I also said it in words. So we can go ahead. A critical point of a functional is a solution of the Euler-Lagrange equation. We say that it is stable if the second variation of the functional at the critical point is greater or equal than 0 and unstable otherwise. The stable solution may be an absolute minimizer or maybe not. And we have examples. But every absolute minimizer is stable. So the class of minimizing minimal surfaces is smaller than the class of stable minimal surfaces. Minimizing means absolute minimizers. It's a larger class. So we can still imagine another conical surface. Let's keep with the two wires. It's a very nice example because I could still imagine a surface in black that goes through the origin. But this you will tell me, no, this guy has is not a minimal surface because it doesn't have zero mean curvature. No, of course not, because here at this point, the curvature like this in the cone is positive and in the other direction is 0. So it has positive curvature. But if I had one more dimension and instead I was in R3, I was in R4, do you see this point that rotates like this? Can you imagine now this point rotating in another dimension? And making the same circle, and therefore having the same curvature like this, but with another sign? In fact, it's almost a proof that it must have zero curvature, because the thing that happens here, it happens there. So, it's very easy to compute that in even dimensions, the Simon's cone, x1 squared plus xm squared equals the other half of the variable's squares, has zero mean curvature. It is a minimal surface in R2, in R4, in R8, in 6, R8, R10, R12, all the different dimensions. In odd dimensions, there are also cones. And you have to put a constant here and separate 3 variables here and 5. No, 3 and 5. 3 and 4, 7, or whatever. And you put that. And you change a little the opening. Okay, you change the opening. Okay, so not here, not here, but in R4 already, maybe the soap wants to do something like this. What does it do? The catenon, the disks, or this? And this was the work of the 50s and 60s by many mathematicians, very important contributions in differential geometry and in PDEs. And you'll see now some names. Let's start by the theorem of Bombieri, De Giorgi and Giusti, 1969. What was it? It was, well, functional analysis, 1906, the Pollevi. Then 1956, De Giorgi and Nash, that's it. And now we are 10 more years, okay? More or less. In dimension 8 and higher, the Simon's cone is a minimizing minimal surface. and only in these dimensions, because Amgren, I think the Georgia also dimension 3 did something, and then finally Simon's 4 surfaces up to dimension 6, because this surface in R8 has dimension 7. You are in R8, the Simon's cone has dimension 7. If the surface has at most dimension 6, all stable minimal cones will be planes. They cannot have a singularity. And as a consequence, all minimizing minimal surfaces up to R7 are analytic, and they don't have singularities like a cone. So up to R7, something happened, and then up to R8, the minimizers may have singularities, okay? So there is a, why is this? Why do you, in high dimensions, you want to go through the origin? The only reason I can explain, roughly, very roughly, but that at the end it's the reason, and it's the reason why the hard inequality has a constant that it is bigger and bigger as the dimension increases. If you want to think variationally, is that if you look at volumes or whatever, or areas, if you want to think of areas in polar cone, imagine that, in fact, the Simon's cone, do you agree that it has many symmetries? All this is radial, and this is radial. There are 2 radial variables. Okay, let me call them S and T, following my 2M, M, Jacobian, M minus 1. The other radial variable, M minus 1, ds, dt. To say that cone, I don't even need angles, because everything can be written in terms of S and T. You see what happens when M increases, going through the origin, the Jacobian is smaller and smaller near the origin as M increases. So it is cheaper to go through the origin. And that's a reason, variational reason. And that's the reason why the Hardy constant. Then you have to do the algebra. And if you ask me why dimension 7 and 8, and then in the same linear case 8 and 9, I cannot give you an answer. That's just computing. Okay. So this is the late 60s, and these are very important theorems. So from minimizing minimal surfaces, you know everything. Up to dimension, if they are up to dimension 6, they are smooth. And in dimension 7, there are non-smooth ones like conic. Open problem, still now. Are all stable minimal surfaces in Rn plus 1 smooth if they are of dimension? If they are of dimension, the surface is of dimension 4, 5, 6. This is an open problem that these are Fields medal open problem, okay? If you are under 40, if you prove this, you have the Fields medal automatically, say. This is, many people like to prove this. Listen, the history, amazing. It was known only for 2-dimensional surfaces in R3 for many, many years, independently by these people in 1979. 10 years after the development for minimizing minimal, and now just 2 years ago or 1 year ago, 2 years ago, and a beautiful paper by Shodosh and Lee that you can find in archive for 3-dimensional stable minimal surfaces in R4. 3-dimensional, and they are missing 4-dimensional surfaces, 5 and 6. And just to finish, if you give me 5 minutes, because I think I started at 4:05. Let me just describe very quick, what we do in this paper, which is the original paper, but with Alessio Figali, J. Rosdon. Okay, this is a problem that I learned from Rezis when I was a postdoc in Paris, 1996, and that he was very much interested in that problem. And he put us and many other people to work, including Juan Luis and myself, because Rezis is very good on this. When he thinks that there's something can go to an interesting directions, he doesn't hesitate, and he has very good eye, right, Juan Luis? And he did with Ginsburg-Landau, And then after Ginsburg Landau, he did with this. But this turned out to be a difficult problem. And so I worked with this problem from 1996 up to 2020. So it took 24 years to solve it, but now it's completely solved, okay? And of course, for the young people, you need to have affordable problems, right? To make a living. Nierenberg used to say, I made a living out of the maximum principle. Made a living means ganar un salario, o sea, ganarse esto out of the maximum principle. But then you can also have a difficult problem, okay? And then my advice is, okay, be patient. You have to be very patient, let it repose and come back, right? And share it with the strong people if you feel that you cannot make it, right? So these are not the only people I share it with, huh? But at the end, we succeeded. So let me tell you the story very quick. It's another functional of those of Hilbert. And now I come back to the Dirichlet energy, but I add a potential energy, like classical mechanics, right? Classical mechanics. If you make the Euler-Lagrange equation, you find the reaction-diffusion or semilinear simplest equation in the elliptic case, in a domain of Rn. Okay, the equation is the first variation. The second if you do the second variation, what you get is the first variation of the equation. The first variation of the equation is the linearized operator, and the linearized operator is minus Laplace minus f prime of u. And being a stable solution, this is a definition. Being a stable solution simply means that this operator that with a second order term and a zero order term is a non-negative operator in the Dirichlet sense. It means that this quadratic form is non-negative. You have this inequality for every function that vanishes on the boundary of omega. So in this problem, we count with two things. First thing, the equation, and second thing, if you have a stable solution, you have a further information, which is the stability, which is this relation here. Well, the model nonlinearities that we had in mind from Gelfand and Barenblatt are these ones. If you want, think of the exponential. And in the exponential, u is not a solution, lambda positive. 0 is not a solution. So minus Laplacian of u equals lambda exponential of u. This is called the Gelfand problem, right? Is there a solution? Trivial solution? No, 0 is not a solution. If you don't have a trivial solution, what do you do first in the calculus of variations? Try to find an absolute minimizer. Can we try to find an absolute minimizer? No, there is no absolute minimizer, because the Dirichlet energy is quadratic, and the potential energy goes with the minus sign and goes exponentially. So the function is unbounded below. So, no trivial solution, no minimizer. In minimal surfaces, usually there is in general, there is a minimizing minimal surface. But here there is not a minimizing structure. But there are stable solutions. And this was discovered by Gelfand, right? And then Barenblatt disseminated Gelfand's ideas, writing a beautiful notes. Up to a certain parameter, there are stable solutions, and if I put in the heat equations, these are the ones that this is a modeling combustion theorem, and this I will see. And this how it would be how this room that it's at 0 degrees initially, it starts heating up because of a reactive problem, okay? And if lambda is bigger than lambda star, then there will be ignition, and from 0 temperature, everything would burn. All the combustible would burn immediately and instantaneously, right? And in this respect, there was a beautiful theorem very good theorem, very, very, very innovative and very, very nice of Juan Luis and Ireneo, that was related of what happens when lambda is really bigger than lambda star for the exponential, right?
Let me tell you, we had one paper that was very good.
Very excellent paper, yes. And Precis always mentioned that paper, of course. So now, what are the enemies? Now you want to go to Hilbert. Are solutions regular or not? Well, what are the enemies? In minimal surfaces were the conic surfaces. Now the enemies will be solutions that blow up at some point, right? because they will not be regular, they will be singular. And this is the drawing. And this will be the problem, and we can put zero boundary conditions. And then you realize that as in minimal surfaces with the Simon cone, there is an explicit guy that solves a beautiful equation, the Gelfand equation with certain parameter, and then you check when it is stable, and that's very easy to check because the exponential of u is going to be 1 over x squared times this constant, and that's a Hardy operator, and when you compare this with the Hardy constant, you find that this solution is stable for dimension 10 and higher. So in dimension 10 and higher, there are energy, beautiful, weak solutions that are singular and stable. And then, very quick, this is a computation. And then Crandall and Rabinovich did the main work in the 75, proving that the dimension 9 is good in every domain, not only in the ball, but in every domain for the exponential or for the powers. And then later, after that, there was a gap. There was no work for, well, there was work on the P Laplacian and other equations related to this. But for the Laplacian, there was no big advance until Bresis retook the problem because of similar results in the parabolic case, 90 something. And the question then was, is this dimension 9 the correct one for other nonlinearities? Or we can construct a counterexample and construct a singular. And in the beginning, in fact, Bresis put people to work to build a counterexample. So it was not clear. And there were other advances by a student of Bresis, in the radial case by myself and Antonio Capella, and then by myself in 2010, that the answer that was good, up to dimension 4. And then in the theorem, and I finish here with Alessio, Xavier, and Joachim, what we prove is that up to dimension 9, so the correct dimension, if the nonlinearity has a sign, that's the only assumption. Every every energy weak solution will be regular. Or if you want, we prove an a priori estimate for classical solutions, which are stable solutions, which is beautifully looks like a linear. The equation is non-linear, but the estimate looks like linear, and it's a Holder estimate, like in the Georginage. Here you have a very weak norm, the L1, and thanks, and even if the problem is non-linear, you prove this thanks to the stability. Thanks to the stability. And well, let me just say that this one main computation, this follows from a main computation that I already knew in 2013, that I did by myself in 2013, and I brought the dimension 9, and as I explained yesterday in the mini course, the dimension 9, but and implied BMO or LP for every P up to dimension 9, but not at infinity. And I was, but I never wrote this because I thought that we were very close, okay? It was 2013, and then I spoke the problem with certain people, 5 or 6 people, very strong, but we didn't succeed. Then I went to Zurich once and Alessio didn't know this problem. When I went the first time to 2018 to Zurich, and he got like, let's go for it. He would come every day to my office. So I was very happy, of course. Then I went back to Barcelona. We didn't solve it. I went back to Barcelona, and 2 years later I came back to Zurich, and I'm very stubborn, and I tell them, please, Alessio, and let's Joachim and Xavi, that knew the problem, because they were my students, should come also to make all the possible brute force. And then after 3 days, we solved it, and we were very, very happy. So that's the story. Sorry for the 5 extra minutes. Thanks a lot for your attention.
Questions? Comments?
Okay. Beautiful talk. ¿Se puede hablar en español? Beautiful talk. I like to be here listening to this presentation of something that first a joke. there is now in these authors, Cabré, Figali, Rosso, Serra, la delantera del Barcelona. Cabré, well, there's a problem with Rosso.
No, la cadera Figali, ¿por qué?
Cabré, Figali, Ross o Tony Serra. Delantera del Barcelona para el futuro. Okay, now for the mathematics. In this department, it was interesting that the linearization of the Gelfand problem around the log gave us a stability condition, the Hardy. And then Ireneo developed a lot of love for Hardy.
Yes. This book is about Hardy,
and this is inside this book, so it is beautiful. There was another branch that is not your branch, but it is related to Hardy.
Yes, and Fernando contributed also, and he had some Calderon-Zygmunt theory, right, related to the Hardy operators.
Now that you have solved this problem with all of the F's for n equals 9, what is the new frontier for you?
Okay, the open problem. Thank you very much. That's a very good question. There are very difficult open problems, but like that, if for instance, if f greater or equal than 0 here is needed or not, okay? Because in dimension 2, 3, and 4, you don't, and 5, we know that this is not needed, okay? To have the estimates like this. But dimension 6, 7, 8, and 9, it is an open problem. These are difficult. But the two main open problems are two. First, that should be possible to do in the 21st half, in the first half of the 21st century. Right? Estamos en 23, quedan 22. Sí, quedan 27 años. First, for the P Laplacian, we have the analog of this theorem with the right dimension. For every P, there is a critical dimension, n, that is explicit, depends on P. For P bigger than 2, we are able to prove the analog of the theory and to prove this result. For P between 1 and 2, it is open. We have a critical dimension, but it's not the correct one that we know from the work of Ireneo and Jesus, and from other works, in the radial case later, or the work for the exponential, that is the correct one for the P Laplacian and P between 1 and 2. And this, Lesio also got very, this was during the pandemics, because we finished this paper right before the pandemics. I was in Bath, and we put it in archive in July, June or July 2019. And we had not decided where to send it. And the people of differential geometry, because they are clever, these guys, huh? They knew that there are because in the proofs and things there are connections with the minimal surface theory, right? And the stables. And they told us the day after putting in archive, they told us, why don't you send it here? And I said, okay. We said, okay, it's good for us. So we were very lucky. That's why it got published very, 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 very quick. And I was saying that after that, during the pandemics, I tried with Lesio, in fact, you suggested that also, well, I mean, both of us, to try the P Laplacian for P between 1 and 2. Well, no, at the beginning of the pandemics, I did the theory with Pietro Miraglio, my student, and Miguel and Manuel Sanchon for the P Laplacian, during the pandemics. A little before the pandemics and during the beginning of the pandemics. And it was optimal for P bigger than 2, not for P less than 2, and then with Alessio, we tried and we didn't succeed. And a new idea is really required for P between 1 and 2. And then this one problem, and the other, my favorite open problem, is the fractional Laplacian. For the fractional Laplacian, it is only for the Gelfand nonlinearity for the exponential that we know the critical dimension, because now in the fractional Laplacian there is a parameter S, the fractional Laplacian S. For every S, there will be a dimension n, which is the critical one. And we know how to compute it because of a paper for the girlfriend always starts everything, like in your case, right, Jesus, with the Pillar-Plachon, starts that you can do the exponential nonlinearity. And Xavier Rosoton, beautiful paper in his thesis, one of his best, in my opinion, he succeeded to solve the problem for the fractional Laplacian and the exponential nonlinearity and find the right dimension. And you know that it's the right one because when you linearize the Gelfand equation around the explicit solution, you get a Hardy operator, and it checks with the Hardy inequality, with the fractional Hardy inequality. And this should be the right one, but we don't know how to prove it in any other nonlinearity. Not even in the radial case, right, Juan Carlos? Even the radial case is open for the fractional Laplacian and a nonlinearity that is not an exponential. And the critical dimension n that depends on S will depend on it's explicit, and it depends on a relation with several gamma functions that involve n and S. Right? Okay.
Because of the inequalities.
Because of the inequalities.
Yeah.
With the Hardy
So it's solved theory.
with the Hardy inequality.
Okay.
And these are the two favorite.
More questions?
And I just wanted to let you give me 1 minute the story of Nash, right?
I wanted to ask.
Yeah, the story of Nash, because it's funny because it was in a way it's kind of disappointing because everybody was expecting that the Georgian Nash would get the Fields Medal, and they should have got the Fields Medal for that. Absolutely, because it was an open problem that you don't need many people, and 50 years open problem, and of course the Georgie. Georgie, I'm sure he was disappointed about that, and probably Nash also. And the story was that the Georgie did it by himself, right, in Italy, and that Nash had finished his PhD in Princeton in game theory. He got a position in Boston, I don't know if in the MIT, this Nirenberg told me, got a position in MIT, Harvard, or Yale, I don't know. But fortunately, he had a girlfriend who lived in Manhattan, in New York. And Nirenberg told me that he would spend more time in Manhattan than in Boston because of the girlfriend. And then he was bored or something, and he went to Courant and knocked on Nirenberg's door. And Hilbert opened the door and said, and this guy introduced himself, I'm Nash, I heard that, and he said, I heard that there are some good open problems in PDEs, but I have no idea about PDEs, but I would appreciate if you tell me an important open problem in PDEs, and if you give me like an introductory lecture on PDEs, 1 hour or something like this. And Nirenberg was a little surprised, but okay, he's a nice guy, and he did it. And he gave to Nash this problem. The elliptic equations in divergence form bounded measurable coefficients. Then the summer, this was the spring, summer passed by, and in the next academic year course, in the fall, it seems that Nash came again to his office, he knocked, and he says, Professor Nirenberg, I think I solved it. But I need to tell you to check that I didn't do any. And then, of course, Nirenberg said, tell me. And that's the story. And then I don't know why they didn't get the...
There is this thing that Nirenberg said once talking to me. They said, listen, there are 2 things that happened with me and Nash. First thing was very good. I gave him the problem. Second thing was very bad. I knew Italian. I knew of the Georgian. Nash was very upset with this.
Yeah, then when Nash came back, the Georgie had already announced, and Nirenberg knew. I'm sure the Georgie was not a competitive guy, was a big guy, nice, super nice guy. Maybe he was disappointed, but no problem. But Nash was very competitive. Yes. But anyway, this talk is, okay, if somebody feels like having time to look in the literature and all this and contradicts Bresis and Browder, please let us know if this thing is wrong. But from what I heard from Resist, they put a lot of care in this thing. I mean, because this statement that Beppo Levi is the first who realized this. They took it from the papers. It seems I trust it 99%, 1.5. But this shows, of course, where does this everything comes from Beppo Levi. Okay, no big deal. Well, no big deal, but okay, but we should know it, right? I think we should know it. Riz Flechet, yes, Riz Flechet, yeah, very nice, but this is Beppo Levi, and the functional analysis, yeah, okay, why functional analysis? And it's everything to solve the problem of electricity and of gravity. Because Joan Sola-Morales was telling me about Green, Kelvin, and where were the other guys? I don't remember now the group. There were the electricity guys first, and the gravitory to make bridges. Yeah. Stokes. Stokes was the guy who was building bridges. He made one in Paris and fell down, in fact. Stokes. He was in electricity. And in the beginning, it seems that the guys didn't know that they were talking about the same thing. The Laplacian in the beginning, right? The electricity and the gravitational, right? And everything comes from here.
I think that the first person who was very interested in both things at the same time was Maxwell. Maxwell was very good at understanding the whole picture. Yeah.
And Green was British, I guess. Yeah.
Green was British, all of them.
And what was,
all of them bloody good.
But what was he physicist rather, or he was a mathematician, or what? Green
was mathematician, physicist, something like that.
This we should check. This I don't have time.
He was a very practical person.
We should check, because if he realizes the net principle.
Yeah, but
that's something, huh?
Same question can be asked about Newton. He was a physicist.
Yeah, but Newton is before, right?
In England there were people.
If we go to Leonardo da Vinci.
In England there were many applied people at the time, but there was always a possibility of checking the theorems with Stokes. Stokes was very strong.
Do you know that?
Took care of the proofs.
Do you know that Leonardo da Vinci already measured the 9.8 meters squared of second?
Maybe that's for the next colloquium.
Yes.
Let's thank Xavier.
Oye, ya le dije que le vamos a dar una sorpresa, pero no le dijo cuál.
Pues no, yo no dije nada. Muy grande. Sí, muy grande. Ya me lo he dicho. ¿Por qué no me haces la cuenta? Igual hacemos más. Es que esta desigualdad es muy. No existe con el producto. Me la inventé, digamos, ¿sabes?
¿Te parece que hacemos
Un placer. Sí que me la he currado, son horas, ¿eh? Hay notas. PDF. Estás invitado.
Bueno,
cuando quieras,
espera, así que
quedamos como en 3 minutos.
Perfecto. Sí. Ah, muy bien, me alegro. Sí, me alegro que haya sido útil. Sí, gracias por venir. Sí.
No, pero prefiero
Ya. No.
¿Por qué menos adaptable a otros programas? Con la ecuación parabólica has de... Es muy buena pregunta, tío. Es muy buena pregunta. Vamos a preguntar a Juan Luis.
Si estamos aprendiendo que decimos que no, ya está. Yo no soy el jefe de la...
Vale, me vuelvo, lo intento. ¿A qué hora salís? ¿Ahora
Ya, a la media de
Dice siempre yo en la oficina y con la cartera.
Sí, si puedes ir tú, voy a intentar
implementarlos para los y la de Nash no la ves. Estoy de acuerdo contigo. Dice por qué.
Vale, pues...
porque es parabólico.
¿Y?
Ahí la gente hace elíptico primero. Y no se aprende el elíptico. Pero nosotros que vivimos del parabólico sí que no sabemos nada.
Pero ahora la buena pregunta para decirle, porque se ha salido un poco por la tangente,
Sí.
es decirle, ¿habéis intentado hacer alguna de las que se hacen elípticas quizás más fácilmente con el parabólico?
Eso es lo que intentaron Phelps y Struck y les salió que para el parabólico es interesante, pero no añadía gran cosa al elíptico. Pero eso, por Phelps estuvo ahí trabajando con Struck varios veranos. Y no encontraron, es decir, lo más fuerte en el elíptico es claramente y después la parte operativa, que es tan fuerte para los analistas que hacen números, los calculistas, que somos muy calculistas todos, es Moser, porque Moser es calcular,